Assalamu alaikum. Welcome to the second lecture of chapter 11. Of course, the chapter is on ceramic materials. As usual, we will initially quickly review what we covered in lecture 1 of chapter 11. Today we will continue the linear density in ceramics, and we will do an example on that. Then we will cover planar density in ceramics. Again, we will do an example on that. And finally, we will cover the third crystal structure in ceramics, the zinc blende crystal structure. And to understand it in detail, we will go through an example. So let us see what you did last time in lecture 1 of chapter. Last time we introduced what are ceramics. We told about the ionic and covalent bonding in simple ceramics. We talked of the electronegativity and its effect on the types of ceramics that are formed, some other simple ceramic crystal structures. We talked of the coordination number and the radius ratio and the critical minimum radius ratio required for stability. We showed you this table of different structures where the coordination numbers is 3, 4, 6 or 8 for ceramics. We did some problems. Using the geometry, we can define our own values for the critical minimum radius ratio. We did some more problems, right? Then we started talking of the crystal structure for ceramics. So we reminded you of the FCC, BCC and HCP structures from chapter 3 on crystal structures, the details of the BCC structure and of the FCC structure. Then we started with the first category, the first type, the first class of ceramics. One of them is cesium chloride and many others are like it, and it is basically a BCC type crystal structure with coordination number 8. And we described this to you. We solved a problem about this. We gave you the structure and how to do the calculations and so on. And then we actually calculated and we found the atomic packing factor. So this is where we stopped. And now we will cover some other crystal structures which are there in some of the more common ceramics. Then we started the second class of ceramics, sodium chloride crystal structure, and I asked you to be surprised, right, and wonder that the common salt you eat every day is a ceramic. We solved a problem on the calculation of density of a sodium chloride ceramic, explained through the figure, and then the details of that solution, further details of the solution where in the end you find the density of the sodium chloride. So that is where we stopped last time. Let us now start the second lecture of this chapter. Now, before we go back, go on, we remind you this is from chapter 3. This is from chapter 3. The direction indices, remember direction indices, right? 1, 0, 0, 1, 1, 1. So these are the direction indices. Okay. So without going any further, we just do this problem. Calculate the linear density of calcium oxide, calcium and oxygen ions. Now, okay. In the 1, 1, 0 direction, in the 1, 1, 0 direction. And they are saying that calcium oxide has the same structure as sodium chloride. And the ionic radii for calcium is this and for oxygen is this. So what is the problem? Write it down. Don't go further. Take a blank page, write it down. You want to find the linear density. Linear density. Your ceramic is calcium oxide. Calcium oxide is the same in structure as sodium chloride. And the atomic radii for calcium and oxygen are given. Okay. So now you have to try to remind yourself what is linear density. linear density. It is the number of atoms intersected by the line divided by the length of the line, right? Linear density. So that is it. And then you know it is sodium chloride type of a structure. Sodium chloride type of a structure. So therefore it is the face centered, but it is calcium oxide now, calcium oxide. So for example, take any one face, but before you do that, the direction here is 110. So draw a simple cube with 0, 0, 0 at the back side of the cube, and you move 1 in the x, you move 1 in the y, and you move 0 in the z. So you have 0, 0, 0 point, and you have 1, 1, 0 point, and you draw the line. So you will see that this line is the diagonal of the base of the cube, diagonal of the base. So this line cuts what atoms and so on. Okay. So try to do this yourself, and please, as always, if you want to be really good in quizzes and exams and the course, then do not go further in the lecture. Just solve it yourself. And when you are totally sure, then you take up the next page. Okay. So now we will go to the next page. So I told you this is the diagram. This is the cube. This is the 0, 0, 0. So 1 in the x, 1 in the y, 0. So this is the 0, 1, 1, 0 point. So from 0, 0, 0 to 1, 1, 0. So this is the line. This is the line. And this is the diagonal of the base. We know that this is, you see, this is A, right? This is A. So therefore this diagonal is root 2A. We know that, right? So the length of this line is root 2A. Root 2A. And what was A for any sodium chloride type? Remember, 2 small r plus 2 capital R. That was the thing, right? So 2R of calcium, 2R of oxygen. That is there. And the definition is here. And how many atoms? One radius of this one, one radius. So 2 radius means 1 atom, right? And then this is 2 radius. So total how many full circles are there on this one? 2. So 2 equivalent atoms. 2 equivalent atoms divided by the length of the line. Okay, so let us proceed further. So whatever we told you, you can read this later on. A is equal to 2, R of calcium, R of oxygen. Put in the values. A is equal to 0.476 nanometer, right? And there are 2 atoms per line like this. This is the length of, this is A. This is A. The length of the line is root 2A, right? Length of the line is root 2A. So root 2 into this A. And there are 2 atoms on this line. So 2 there and root 2A here, and whatever number is comes out to be. So the linear density is so many ions of oxygen per nanometer. So many ions per nanometer of oxygen and so on, right? Now you should solve the same way using the geometry for calcium also. But I will try to do the same chemistry balance, that if it is calcium oxide, there is 1 of calcium, there is 1 of oxygen. So whatever density is there for calcium will be the same as it will be for oxygen, because calcium and oxygen are balancing the valences into +2, -2, +1, -1 and so on. 1 calcium and so on, right? So it will be the same. It will be the same, right? So therefore that is there, but you can try to solve it and you will find it that the density of the other one, right, is also the same. So this was about linear density. We have done atomic packing factor, we have done density, we have now done linear density. What is left? Yes, you are right. Planar density. So let us see if they are trying to do that for us after this. Oh yes, you see, this is from chapter 3 again. This is chapter 3. And this is Miller indices. Miller indices are for planes, right? So if you can see the 100 plane, the 110 plane, the 111 plane, and so on. Miller indices. You have to quickly remind yourself that how are these Miller indices given. You try to find out the intercept on x-axis, y-axis, z-axis. You invert whatever value you have, and you write the Miller indices and so on, right? So very quickly you try to revise that if there is a plane identified by giving the Miller indices of the plane, then how do you draw this plane and what are the Miller indices and so on. This was chapter 3. Once you have revised this, then you can come back to chapter 11 and do some planar density type of problem. So okay, the the ceramic is still calcium oxide, which means that the structure is sodium chloride, but we are asking to find the planar density this time. Planar density, and the plane is 1 1 1, the 1 1 1 plane, 1 1 1 plane, and of course the radius of calcium and oxygen ions should be given. So again, do not proceed further in the lecture. Pause it here in the video lecture, take your pen and pencil and start doing this. The given is that you have calcium oxide as the ceramic, which has the same crystal structure as sodium chloride. We want here to find the planar density of calcium oxide, which is the unknown, and the knowns are the radius of calcium and oxygen ions, right? So how will you start again? The definition of planar density is the number of diameters or number of atoms on the plane intersected by the plane divided by the area of the plane. So that is the definition of planar density. And again, you draw a simple cube and you draw the 1 1 1 plane on that, and then you try to find out how many planes are there. In that plane, how many atoms are there? So planar density is number of atoms cut by this plane upon the area of this plane, right? So let us see how it does.